Hello everyone. In the last videos we covered the root finding techniques for curves. Now we are proceeding with the interpolation methods. In mathematical field of numerical analysis, interpolation is a method of constructing new data points within the range of a discrete set of known data points. In engineering and science, one often has a number of data points obtained by sampling or experimentation, which represent the values of a function for a limited number of values of the independent variable. It is often required to estimate values at some other intermediate points of the independent variable. To obtain such results, interpolation techniques can be used that would yield approximate values. If estimation is done in the interval such that the point lies outside the given values, then it is called extrapolation. To make more familiar about interpolation, here an example is given in which there is some sample. Here the values corresponding to x shows the years and the values corresponding to y shows the population in lakhs corresponding to those years. By interpolation techniques, we can estimate that the population at any year lying within the range of given samples or even out of the range. The given x's values in samples are called arguments and the y's are called entries. There are many types of interpolation: Newton-Gregory forward difference interpolation, Newton backward difference interpolation, Lagrange's interpolation, Newton's divided difference interpolation, and spline interpolation. Now we are proceeding with the Lagrange's interpolation. Lagrange's interpolation is used for the data set where the arguments are not equidistant and also for that are equidistant. The arguments, that means the values of x's, can be either equidistant or maybe not. Lagrange's is applicable to both the cases. The Lagrange's formula can be given as y of x is equal to the sum of products of Lagrange's coefficient and the corresponding yi. Lagrange's interpolation formula is applicable when an argument is given and corresponding to which an entry has to be found. In some cases, it also happens that an entry, that is the value of x, is given for which the value of x, that is the argument, has to be calculated. In that case, we'll use the Lagrange inverse interpolation formula. So the expanded version of Lagrange's interpolation formula is this. Further moving to, here the value of x is that argument for which corresponding entry has to be predicted. Further moving to Lagrange's inverse interpolation. As the name suggests, this is just the inverse of Lagrange's interpolation formula. Here an entry is given but a corresponding argument, that is x, for a given y has to be predicted. For that, we will replace the x values in Lagrange's interpolation formula with the y values, and similarly the y values with the x values. Now let us go through the program for these interpolation methods. This is a program for the Lagrange interpolation. Here we have an x data set for number of temperatures, that are the experimented values, and for the corresponding temperature we have the pressure that is related to that temperature. These are the experimental values, and we are asked to estimate the pressure. That means the entry or the Y at the argument or the temperature 372.1. That is, the pressure at the temperature 372.1 has to be calculated. For that, we are using the Lagrange interpolation formula. Here, the while loop runs for the number of iterations. A single while loop will calculate this much of term and the number of samples, and will run for different number of samples. Within this while loop, this product will run for a single Lagrange's coefficient. These Lagrange's coefficient are multiplied with the corresponding entries and are summed up finally to yield the y of x. Let us run this. So here the interpolated y is this, that is the pressure corresponding to the temperature 372.1 is 177.8304. Now let us consider a program for inverse interpolation. Here there are two data sets experimented, that is for x and y, and we are asked to estimate the value of x for a given y. Here the entry is given, and we have to estimate the argument, that is the x's value. So the loop runs as the same. Here we have replaced the x value with the y value. In Lagrange's interpolation, we use the x, that is the argument. Here in inverse interpolation, we are using the entry. Here also. So this will yield the argument for corresponding entry 13.2. We are running this. The interpolated x for 13.5 is 97.65582. We can compare this. For 12.80, the argument was 96.2. For 14.70, the argument is 100.0. And we have calculated for 13.5, that is, this will lie between 96.2 and 100.0. This is how the Lagrange's interpolation works. Thank you.